GeoVision3D is a high-throughput three-dimensional image informational model for geomatics professionals. A development project proposed and presented by Pentagram Research Center Private Limited, Hyderabad, India. This presentation is an intellectual property of Pentagram Research Center Private Limited, Hyderabad, India. No part of this presentation should be copied or reproduced by anyone in any form or any kind for any commercial use other than our authorized personnel or agencies. This presentation is produced by me, Rajan, the founder president of Pentagram Research Center Private Limited, Hyderabad, India, and the technical director of Pentagram Labs LLC, USA. Technically supported by Mr. G. Satya, New York, Dr. G. Ramesh Chandra, Hyderabad, India, Mr. Pat Krishnan, Managing Director of Pentagram Labs LLC, USA, Ms. G. Prashanti, Hyderabad, India. The graphic supported was extended by Mr. Yashasvi Vemuganti, Hyderabad, India, and the commercial support by Dr. Michael Coyle, the Managing Director of Avatar MedVision US LLC, North Carolina, USA. Three-dimensional digital image processing is an important area of research that has numerous applications in the fields of medical imaging, seismology, geomorphology, remote sensing, and material sciences. Depending on the requirement for solving a specific problem, one has to identify various features of three-dimensional images while applying suitable algorithms. For example, the quantitative analysis of geomorphological structures in GPR radargrams and other similar images requires extraction of volumes and shapes of geological constructs like oil reserve, ores and minerals, and encapsulated gems, gold and diamonds present below the Earth's surface. In order to do this, there is a need for an aerial survey of the area of interest for locating the land for scanning with the help of ground-penetrating radar. It is necessary to drill a hole to obtain crude oil and natural gas from under the Earth's surface. Engineers make this hole using a rotary drilling rig. The rotary drilling rig uses a drill bit to cut through the earth and create a hole. As the hole gets deeper, pipe is added to the drill bit to allow it to dig further. These lengths of drill pipe form the drill string. This pipe is connected to an engine that turns the drill bit to cut the hole. The rotary rig operates the same as a handheld electric drill. The electric drill has a motor that turns the drill bit, and sufficient weight must be applied to keep the drill in contact with the bottom of the hole. There are four major operations in a rig: hoisting, rotating, circulating, and power. The hoisting system is used to raise and lower pipe in and out of the hole and to support the drill string to control the weight on the drill bit during drilling. The rotating equipment turns the drilling bit. The drilling operation uses fluids to reduce friction and remove rock fragments or cuttings. The circulating system pumps these drilling fluids down the hole, out of the nozzles in the drilling bit, and returns them to the surface where the debris is separated from the fluid. A drilling rig needs power to operate the circulating, rotating, and hoisting systems. This power comes from two or more diesel engines. Power is transmitted to the drilling rig from generators that provide electricity. High drilling cost. Yes, indeed, this is a serious problem. Drilling is usually done by a service company or drilling contractor. The drilling company operates in accordance with a contract which specifies that the well will be drilled to a specific depth. The contractor is paid on a per day or per foot drilling rate. In the year 2007, it cost $4 million to drill an oil well and $3.9 million to drill a natural gas well. The average cost to drill a well was $574 per foot of depth. The average cost to find and develop an oil and gas property in the United States was $17.01 per barrels of oil equivalent, that is BOE, from 2005 to 2007. The cost of onshore development was $13.38 per BOE, and for offshore development was $49.54 per BOE. Based on some statistics, 1 out of 5 rigs drilled in an area yields oil recovery. This means $20 million has to be spent for prospecting and locating one oil well. How to read hydraulic cost? Is it not worth trying all possibilities of reducing the cost of locating an oil well to just $4 billion and save $16 million? Well, this presentation is indeed aimed at showing such a possibility. We propose a state-of-the-art project called GeoVision3D. The major objectives of this project are to develop new methodologies for data acquisition, processing, and interpretation, to integrate multiple technologies focusing VSP, that is vertical seismic profiling methodology and interpretation that guide discovery of new oil reserves, oil field development and management for maximum economic oil recovery. To make use of VSP methodology for prospecting mine field development and management for maximum economic recovery of various minerals and gems. The sub-objectives that are incidental to the major objectives are to devise methodologies for collecting data from underground of the earth crust, data acquisition sensors like synthetic aperture radar or ground penetrating radar and microwave pulse transmitters could be used to achieve this. Other seismographic techniques could also be used alternatively or in association with SAR or GPR. Multiple sensor fusion is the next part. Data collected from various sensors could be integrated as a data set from which quite a lot of information about the subsurface elements could be interpreted. Fast and reliable algorithms for extracting information from the data set is a major R&D component involved in this project. To develop an artificial intelligence-based expert system software package as an integrated component with a given geodata processing requirement. Miners, civil engineers, and archaeologists would find this package very useful. To develop a state-of-the-art technology to use the above tools for detecting oil, minerals, and gems reserve in a particular area from which genuine and reliable data set has been collected. As a part of this project, a few people would be trained in the state-of-the-art operational methodology of oil exploration. Let us consider a minefield model shown here as a rectangular as well as hexagonal pattern. Rectangular model is generally preferred to avoid operational difficulties. The rectangular field model is divided into a matrix of 11 by 9 subregions. Scanning of a minefield is carried out using a GPS-controlled autonomous mobile robot AMR system consisting of a ground-penetrating radar and image acquisition system. Serpentine scanning is used for prospecting minefields. The proposed AMR would consist of a ground-penetrating radar, global positioning system, control and guidance system, communication system, power supply, vision system, and chassis. The ground penetration radar is used for excitation. Excitation is applied at appropriate locations, preferably at the centers of the subdivided regions. Area of a subdivided region determines the resolution. The intensity of excitation depends on many factors, but mainly on the required depth of penetration. A short duration pulse is applied as excitation and the echo received and registered for further analysis. With reference to the minefield model shown, one would obtain 99 echoes in the form of one-dimensional characteristic signals. The excitation by the GPR is applied at every predetermined point whose coordinates, that is the latitude and longitude, are obtained from the GPS. The excitation is applied to the fashion shown here in this slide. The intensity of excitation depends on many factors, but mainly on the required depth of penetration. A short duration pulse is applied as excitation and the echo received and registered for further analysis. With reference to the oil field model, one would obtain 99 echoes in the form of one-dimensional characteristic signals. One such signal in the analog form is shown here. The sampling of the analog signal is carried out with the Nyquist frequency without causing any loss in the vital information related to the characteristic echo due to various subsurface elements. The sampled and discretized signal is shown here. The data acquired in this way will be a collection of one-dimensional sequence of numbers pertaining to the characteristic signals from different sample areas in a field of interest, echoed due to a particular excitation type. This slide shows a simple representation of the ensemble of data. Note that there may be a requirement for collecting data due to more than one excitation type. What is required now is to predict the signals for the neighborhood of each subsampled area. This figure shows one such model of the predicted signal data, which amounts to a 3D array, that is a 3D image. We call this image as a vertical seismic profile. This slide shows the elevation and right side full section views of the VSP stack. VSP refers to vertical seismic profile. VSP is also known as sectional profile. That is it, VSP stack. HSP refers to horizontal seismic profile. HSP is also known as a depth slice or time slice. This is the time slice stack. VSP stack is generally used to predict oil and other mineral reserves, whereas HSP is used for archaeological survey. Individual lines of GPR data represent a sectional view of the subsurface. Multiple lines of data systematically collected over an area are used to construct three-dimensional images. Data may be presented as three-dimensional blocks or as horizontal or vertical slices. As I already told, horizontal slices also they are known as depth slices or time slices. They are essentially plan view maps of specific depths. Time slicing has become standard practice, especially in archaeological applications, because horizontal patterning is often the most important indicator of cultural activities. Now, this slide shows the first 14 depth slices through a burial site in Japan. The survey was made in November 1993 using an analog GPR equipment. This slide shows the animated view of 2D slices of the 3D radargram obtained at the Nutubaru Kofun burial site in Shintomi-machi, Ishikawa, Japan. The depth slices are obtained using an analog GPR system and the data processed using GPR Slice version 7.0 software package. The large round anomaly found at various depths, see for example here, are the reflections from the moat of a destroyed burial ground dating from the 6th to 7th century AD. The full description of the history of this mound could be seen in various literature. This slide shows the Nutubaru Kofun excavated burial site in Shintomi-machi, Ishikawa, and the exploded view of the moat. We acknowledge Geophysical Archaeometry Laboratory Inc., California, for providing details about the material presented in the previous 3 slides in their website www.gpr-survey.com. Project GeoVision3D would be carried out in 2 phases. Phase 1, prediction of unknown data from known 3D radargram. Phase 2, subsurface truth evaluation. Phase 1 is about the data interpolation of a radargram. Consider a land area of 1 hectare, which is equivalent to 10,000 square meters. This is a grid model of 1 hectare of land divided into 100 subregions. Each subregion is of 100 square meter area. Each subregion is excited with a pulse transmitted by a GPR and the corresponding echo recorded for processing. Then an ensemble of 100 echoes would be recorded. Let the subsurface earth volume to be prospected be 100 by 100 by 100, that is 1 million cubic meters. Each 2D depth slice would then be of size 10 by 10, that is 100 square meters. Based on user's requirement, the number of depth slices could be fixed. For example, if the user requires data sampling of 1 voxel per 10 by 10 by 10, that is 1000 cubic meters earth volume, then the number of depth slices required for prospecting 1 million cubic meters of subsurface earth volume would be 10, 1 for every 10 meter depth. Now, the 3D radargram size would be 10 by 10 by 10. Note, this radargram of 10 by 10 by 10 is a low resolution data corresponding to 1 million cubic meters of subsurface earth volume. Alternatively, one can think of obtaining a radargram of size 100 by 100 by 100. This means that the subregions of area 1 by 1 square meter is excited with a pulse transmitted by a GPR and the corresponding echo recorded for processing. Then an ensemble of 10,000 echoes would be recorded. The number of depth slices would be 100, and this amounts to saying that 1 million data samples would be acquired to prospect 1 million cubic meters of subsurface earth volume. The radargram would then be of size 100 by 100 by 100, which is quite reasonable in the sense that the information loss would be minimum. It is sufficient to have 1 million data samples for prospecting 1 million cubic meters of subsurface earth volume at the rate of 1 voxel per 1 cubic meter of subsurface earth volume. Alternatively, if one wishes to have finer resolution of 8 million data samples for prospecting 1 million cubic meters of subsurface earth volume at the rate of 1 voxel per 50 by 50 by 50 cubic centimeters, that is 0.125 cubic meter of subsurface earth volume, then the acquired radargram would be of size 200 by 200 by 200. The question that arises here is that given a radargram of size 100 by 100 by 100, will it be possible to obtain a radargram of size 200 by 200 200 with a better resolution? The answer is affirmative. And the phase 1 of this project is all about developing an intelligent algorithm for predicting or interpolating the data set acquired using traditional GPR equipment in the real-time situation. As a solution to this problem, we use an indigenous methodology of 3D morphological dilation using a nonlinear predictor. This predictor has been tested for its robustness and speed. This algorithm forms the core of the entire project. In what follows, I shall present a couple of sample images, their parsed and reconstructed versions using this technique. Let's consider a sample image shown here. Skeletonization is carried out on this simple sample 2D image using an indigenous algorithm. Note that one cannot reconstruct the original 2D image from the skeleton because much of information is lost in the process of skeletonizing. The figure on the right shows approximately reconstructed 2D image from the skeleton. The 2D morphological dilation is used here with the help of a specific structuring element. Note that the dilation has been carried out without the help of prediction algorithm. Let us consider a real-time sample image. Subsampling is carried out on this sample 2D image using the indigenous algorithm. Note that one cannot reconstruct the original 2D image from the subsample 2D image because 50% of original information is lost in the process of subsampling. The figure on the right shows approximately reconstructed 2D image from the subsample 2D image. The 2D morphological dilation is used here with the help of a specific structuring element. Note that the dilation has been carried out without the help of prediction algorithm. Subsampling is carried out on the sample 3D image shown here using our indigenous algorithm. Note that one cannot reconstruct the original 3D image from the subsample 3D image because 50% of original information is lost in the process of subsampling. The figure shown on the right extreme shows reconstructed 3D image from the subsample 3D image. The 3D morphological dilation is used here with the help of a specific structuring element. Note that the dilation has been carried out without the help of prediction algorithm. Now, the skeletonization is carried out on the sample 3D image using our indigenous algorithm. Note that one cannot reconstruct the original 3D image from the skeletonized 3D image because more than 50% of original information is lost in the process of skeletonization. The figure on the right extreme shows the reconstructed 3D image from the skeletonized 3D image. The 3D morphological dilation is used here with the help of a specific structuring element. Note that the dilation has been carried out without the help of prediction algorithm. Now let's take the case of a real-time radargram depth slice and examine the possibility of interpolating the 3D radargram slice for better resolution. This image shows the 2D sectional slice of a 3D radargram, and the corresponding histogram is shown here. The corresponding subsampled image, 50% loss has been introduced in this image, been shown here, and the corresponding histogram also shown here. Now we dilate this sparsed image using a 5 by 5 structuring element and show its histogram. Finally, the reconstructed 3D radargram slice is shown here along with its histogram. This radargram was taken from this website. Now, let me demonstrate the operation of reconstruction from sparsed image. The image of a radargram is loaded. The image is parsed so that 50% loss is introduced. I am duplicating this image, keeping it here. I am restoring the original picture. I am zooming it in. We can see the finer details. I am zooming it in. This parsed picture. You see the sparse 50% loss could be clearly seen here. This parsed image is now dilated using a 5 by 5 structuring element labeled E11337799. And the dilated image shown here. Duplicate this. I am restoring the sparsed picture. Now the dilated image is eroded by a 3 by 3 structuring element labeled E1379. Eroded. I am duplicating this. I am keeping the image here. Restoring the previous image. This histogram of the original image, histogram of the sparsed picture, one can see clearly 50% reduction, the dilated picture and the eroded picture. One can see from the reconstructed image that there is no much of a loss of information in the reconstructed image. But of course there is loss in this dilated picture. You can see the pixel deformation here. That is precisely why I eroded this picture, dilated picture, by a 3 by 3 structuring element. See the histogram of that, the slope of this, the slope of the histogram of the reconstructed picture, and the original image, the slope doesn't change. It means the reconstructed picture is in accordance with the original. This operation is called morphological filtering. The idea behind this filtering is that a given image is parsed with 50% information loss, and the lost information is recovered by morphological filtering. This operation is analogous to interpolation of data in a radargram, so that the size of the radargram is doubled. That is, a given radargram of size W by H by D becomes 2W by 2H by 2D. Phase 2 of the project GeoVision3D is about pattern recognition and 3D radargram. The exploded view of a 3D radargram shown here is obtained using a ground-penetrating radar. Details of the actual site surveyed is unknown. Technical details about the operation of a ground-penetrating radar and its uses in surveying could be found in the literature. The 3D radargram shown here is obtained using a ground-penetrating radar. This 3D radargram shown here consists of 81 VSPs stacked one behind the other. 6 of the 81 VSPs are shown here for the purpose of understanding as to how a 3D radargram is reconstructed from VSPs. Now the first slide of the 3D radargram showing here, the second slide, third, fourth, fifth and sixth. This 3D radargram data has been processed for subsurface truth evaluation using a very valuable state-of-the-art technique for prospecting minefields with a high degree of precision and reliability. The exploded view of the processed 3D radargram is shown here. A complex 3D image processing technique has been used to extract the finer contents of the 3D radargram. A number of filtering operations were carried out on the original 3D radargram shown in the previous slide and the result obtained shown here. The type of filters and the way in which they are applied to one 3D radargram will not remain the same for any other given radargram. However, one can use the set of filters identified for this purpose. 8 of the 81 sectional slices of the processed radargram are shown here for the purpose of understanding as to how ground truth evaluation could be made from a 3D radargram. Now, I'm giving a demonstration of the actual work carried out on this particular 3D radargram. Now I'm loading this GPR 3D radargram. I'm rotating this in 4 pi steradians directions. From this 3D object image, one will not be able to visualize the contents. In order to extract the subsurface truth, one has to go in for processing the radargram. That's what I'm trying to do now. We made use of a series of morphological filters and obtained a processed image which is shown now. I am loading this processed picture, rotating this. This gives a better idea of what is contained in this radargram. Still not clear. One thing for sure, that there is something related to some equipment. Some kind of a construction below which this equipment is placed. Now I'm executing an edge detection operator, 3D operator on this picture, and you get that. Now you see the result of applying the edge detector operator on the 3D image. Something very interesting pops out. It looks like a building, a 3-floor building, below which there's a gamut of equipment. Truly speaking, we don't know what's all about, but we got this by processing the 3D radargram. You can see that staircase there. You can see the walkthroughs, the floors. Number of pipes and tubes. Looks like some motors have been fitted. The below portion is quite dark. Let me try to enhance the voxel intensity. What I'll do is I reload this picture on the left. This particular picture, I'll try to reload this here. Yes, the picture has been reloaded on the left hand side. I'm trying to enhance the intensity, the voxel intensity, especially below this point. I'm adding 30 to each voxel. Seeing on the right here, the voxel intensity have been improved. We are able to see certain valuable information, the details of which we don't know. Let me zoom it in. You can see this staircase here, some equipment, some pipes, some floors here. Looks like a lift, elevator. Now I'm improving this intensity further by multiplying each voxel by 2. You can see the down portion of this image, the processed picture. The question of artifacts doesn't come here because we don't make use of any spectral domain operators. Zooming further in. Trying to rotate to the right. You see clearly the contents, the details of which we really don't know. Well, that's how it goes. This slide shows the software architecture of GeoVision3D. After seeing the demonstration, I would like to propose this GeoVision3D. The architecture will be like this. There will be a plug-in module for oil, minerals separately, gems, diamonds, gold, and rare earth elements. These are the plug-in modules. The GeoVision3D will have a kernel which will have the fundamental 3D image visualization processing algorithms. They're all artificial intelligence based expert systems to prospect, identify, locate these subsurface components of Earth. Well, the uniqueness of this package would be concept to product is made in-house. High throughput algorithms for 3D image visualization and processing. 3D morphological operations and algebra of 3D geometric filters have been introduced by us. The novel concept of electronic sectioning of 3D volume data in 36 directions have been introduced by us. Variable thickness 3D surface detection is an important operation in the process of evaluating the true subsurface Earth volume. 3D texture detection 36 directions. Spatial and spectral domain based 3D volume data segmentation is also included in this package. The technical and commercial advantage of 3D technology used in this package would be academic application, CAD/CAM application, medical imaging application. This 3D technology could be used. And this is called 3D IP core because all other versions and variants would be purely developed based on this core. We are interested in this particular project, an application to subsurface imaging application. Drilling an oil rig is expected to cost $4 million as per literature survey and study. At present, the oil strike possibility is not even 2 out of 5. This means a minimum of $20 million have to be spent in order to get at least oil extraction from one rig. In this context, a 3D IP core could be put to use by plugging in pattern recognition software modules for prospecting oil, minerals, and others. Then, oil strike capability or possibility would be almost 100%. This application together with an AMR fitted with a GPR is an ideal prospective solution or technique. What we intend to do. We wish to make the best use of our expertise in the 3D technology achieved so far to develop the state-of-the-art artificial intelligence-based software system GeoVision3D that will go a long way in pursuit of subsurface ground truth evaluation and hence of the economic development of the entire world. I try to conclude with the following remarks. GeoVision3D would be a powerful tool to visualize and process 3D radargram images. VSPs obtained using other scanners could be visualized and processed with a high degree of reliability. Many unique and significant features which are not available in most other software packages. 3D technology used in the development is technically superior to most other available technology. Speed, precision, and reliability are far above those exhibited by most other software packages. Comprehensive package developed using in-house theoretical concepts, paradigms, and tools. Electronic dissection could be performed with the help of the software and associated hardware. A technological boon to geomatics professionals and civil engineers. Very high social and commercial impact is anticipated. The commercial advantages are a multi-billion-dollar business is anticipated once the global market is properly identified. Every mining engineer, archaeologist, even an individual can afford to purchase GeoVision3D. The 3D technology used in developing these packages could also be used in developing softwares for medical imaging, treasure hunting, defense, and so on. I sincerely thank the listeners on behalf of our project team and the research team. Thank you one and all.